So usually when I give a talk to computer scientists, I tell a story with twists and turns, but maybe in this case I'll tell you up front what's going to happen and go through everything. So this talk is about decidability. So let me discuss the definition. New independent if lambda to the n equals 1 implies m if n is 0 for all integers n m. Okay, so lambdas and mu's in this talk will be integers. So my talk is kind of about some work after a paper by Philipp and Chris Schulz on the decidability of Pressburger arithmetic expanded with powers of 2 and powers of 3. So my talk will be some work built on top of that. So let me state this theorem. The first order logical theory of natural numbers plus as only in order even if it is definable, and then powers of 2 and powers of 3 is undecidable. Okay, so undecidable means provably there does not exist an algorithm that takes a logical statement that involves quantifiers, powers of 2, powers of 3 addition, and then decides whether the statement is true or not. So no such algorithm exists. And why this result is so interesting, one of the biggest reasons for me is that there is a new method for showing undecidability. So usually you show undecidability by proving that you can define multiplication in the structure, and then you reduce from Hilbert's problem, for example, or from Gödel's result that the theory of arithmetic is undecidable. And then there's a separate paper by Schulz that shows that, in fact, multiplication is not definable in this structure. So this new method, it was necessary. So this undecidability requires formulas with 3 blocks of quantifiers. So it does, first of all, it does not require a fixed number of quantifiers, it requires arbitrarily many, but the quantifier alternation depth required to prove undecidability is 3.
So does that mean that for less is decidable, or is it just that this proof?
So for less, that's my next thought I'm going to say is about just exist, but so this proof requires, so exactly which fragment of the first order theory is undecidable? The fragment that allows one to use at least 3 alternating blocks of quantifiers. 2 alternating blocks of quantifiers, we don't know. 4 undecidable. So theorem, this is from 2022, this one is from this year. So it's me, Orion Luca, there is a new thread, and James Worrell, the existential theory of the same structure. Is decidable. So existential means I have just this bunch of existential quantifiers and no the quantifier-free part. So my talk is basically about these 2 results. One is how you show undecidability using this new method. 2 is how you show decidability of the existential fragment. So whenever, for these arithmetic structures, existential fragment, decidability, it's some kind of a number theory problem. So and this is just an application of Baker's theorem and some results from Diophantine approximation. Okay, so this currently what we don't know is exists for us. Is this decidable or undecidable? Okay, but the story does not end here. So this new method of undecidability, it's possible to apply it to other structures. So I'll give you two of these examples. So this one, of course, proposition, because I have to still write it down and publish it. Proposition. The first order theory of natural numbers with plus, and then I add to it now, well, let's do the plus one. UN is undecidable. I'll tell you what UN is, where UN, where UN is an LRS, a linear recurrent sequence over integers with exactly two dominant roots. There's a small extra condition in it that this must be non-degenerate, but I'll skip that. So what does it mean? So UN is a linear recurrent sequence, which is like Fibonacci sequence. So Fibonacci sequence is a linear recurrent sequence with one dominant root, because when you write it as an exponential polynomial, you have one dominant term. So UN is equal to 2 to the n is a linear recurrent sequence with one dominant root, namely 2. So linear recurrent sequences with two dominant roots, they are the next level of complexity. An example of this would be UN equal to 2 plus in plus 2 minus in, well, let's say plus 2 to the n. So these two guys are the two dominant roots. And if we, I'll talk about this later, but if we have a linear recursion with exactly one dominant root, assuming that the characteristic polynomial is irreducible, then in fact this theory is decidable. Okay, so what we do here, we view these guys as linear recurrent sequences. Instead of adding two of them, I add one of them, but I go one level up in the hierarchy of computation. Okay, this is very similar to that, but you can do even a little bit more. So you can even get rid of the plus to get undecidability. So the first order theory of natural numbers is just order, and now I add to it a function that takes n and then maps it to the maximum of n is undecidable. Where again, this is the results. So instead of adding the predicate, the set of values of this, I can add an object with more structure. Here, I can talk about which guy is the nth term of the sequence, and without a plus, I can get the undecidable. Okay, do something more. The first order theory of natural numbers begin with order, and now I add to this a function. So tau is the Ramanujan tau function, so I add it to, instead of the function that takes n and returns un, now takes n and returns the absolute value of the tau function. Tau function is from natural numbers to integers, so it has both positive and negative values. So I take the absolute value to, so that the type checks. So the first order theory is undecidable. So these three results, these structures have very strong Diophantine approximation properties. And the new method of Ramanujan-Schulz is that if you can extract from your structure arbitrary finite sequences of natural numbers in a certain way, then you have undecidability. So if your structure has as a large entropy, if you want to think of it like this. Then it's undecidable. And we use Diophantine approximation in these cases to show that everything that's possible will happen in these structures. So, open problems. Open problems. Okay, I'll just write the structure. So let's take the fruit structure. But instead now let's add two functions. Let's not add plus. Again, this I don't know. Then let's take the numbers again in order and now add the values of the tau function. This also I don't know. So tau function, only the function variant is known to this. Okay, so I will go over this result. The existential theory is decidable, and then I'll illustrate the method to prove undecidability on the tau function example. Okay, any questions so far?
You also said, what was it, that with the primes, you can use this method too and get...
Yeah, so, yes. So you can take natural numbers with a plus and add the predicate for primes to it. So in this there's this, okay, maybe I add section on prime. This is so important. So now the question is this. We've got n plus and the sequence of p and the set of all primes. P prime. Okay, so this decidability of this structure is a famous open problem, decidability or undecidability. So there's this called Dixon's conjecture. So we take a bunch of linear forms, right? A1 x plus b1 am x plus bm with ai bi integers. So suppose no prime divides the product for all x, then all of these forms are simultaneously prime for infinitely many are prime for infinitely many x. So this is the Dixon's conjecture. It's the linear case of Schinzel's hypothesis, so it's a bit more respectable. It's at least called a conjecture. So every result about this structure is assuming Dixon's conjecture. So nothing is known without assuming. And what are the results? The results of assuming Dixon's conjecture, you can define multiplication in this. And this gives you undecidability again in the exist for all exist fragment. But it's not as severe because Hilbert's tenth problem, you have fixed bound on the degree of the polynomial and the number of variables, right? You have undecidability. There are two numbers that give you undecidability. So in the end, you get undecidability for three alternating blocks, but a fixed number of quantifiers. So you can use this new method to get undecidability for two alternating blocks of quantifiers. So it's not as severe in this case because the number of quantifiers is fixed anyway. Yeah, so a big open problem is tell anything about the structure without Dixon's conjecture, and the existential fragment of this is decidable, assuming, again, Dixon's conjecture. Okay, so that's the primes. Did we forget any other important people? Okay, so let me start with this decidability for the existential fragment. So through some not very difficult arguments, you can show that deciding the first order theory of natural numbers with the class and order and number 1 to the n, number d to the n is equivalent to. So now, in the above I have only 2 and 3, but this step works for as many powers as you want. You need to be able to do 2 things. One is to solve a single linear equation in these guys. So solve, not exactly in these guys. So you need to solve ai lambda I to the k times mi is equal to b. So you need to, I give you a k, let's say 10. I give you linear coefficients in, so you're solving this diagonal equation in these guys. So you need to find these exponents that solve this. In this talk, I'll only deal with the case where k is 1. But yeah, so in the result there I state 2 to the n, 3 to the n, but it works for any 2 powers, a to the n, b to the n. So when you try to do 2 to the n, 3 to the n, sometimes we have to solve something in 4 and 9, for example. So all of them are shown to be decidable together. That's how you need to do it. So you need to be able to solve a single exponential Diophant equation, and then you need to solve a system of homogeneous linear inequalities. Solve the system of ai lambda I with k n I greater than 0. So, yeah, you solve a single equation and solve a system of homogeneous linear inequalities. Okay, so I'll talk about this part. This part uses Baker's theorem. This part is not super difficult. To be honest, neither are very difficult in case of 2 and 3. But yeah, so this requires a trick, but there's no general methodology in it. So, okay. So now I'll focus on the case where d is equal to 2 and I have lambda 1 equals 2 and lambda 2 equals 3. So let's start with this one. So suppose I give you an equation a times 2 to the n plus b times 2 to the n is equal to c. This is known as a generalized QI equation. Okay. So how many different solutions do these equations have? This is a very well studied topic, but we are interested in just solving these things. So 2 and 3, so if I have a solution, I will have finitely many solutions in this case. So how do we solve this? We will use a theorem of Baker. But I'll give you a consequence of Baker. I won't give you the full Baker. Okay, Baker. Theorem. So there exists an absolute constant C. There exists constant C is 0 such that for all for all integers lambda mu, well, they don't even have to be integers, for all lambda mu, and then AB rationals, and m integers, I consider A lambda to be n plus B mu to the m, let's call this capital lambda. If it is not 0, then its absolute value is bounded from below by a times the n, the magnitude of that, and n to the minus c, oops, Then here I have a log. I have naive height of A plus naive height of B, and then this to the 4. Okay. So this naive height is just the maximum of the absolute value of the numerator and denominator. It appeared in, I think, since Sebastian's talk, maybe 2 days ago or yesterday. So it gives me almost exactly what I want, right? It tells me that whenever this sum is not 0, it is basically as big as either of these terms. There's a denominator here, but it is polynomial in n. And the important bit here is that the heights of A and B do not play as big of a role. There's a log in front of it. So this will be important. So how do I solve this now? If C is equal to 0, then I make a divisibility argument. 2 and 3 are coprime, so that's easy. And if C is not equal to 0, then the left-hand side basically grows as fast as any of these terms. So quickly, Baker's lower bound will become bigger than my constant C. So I just put Baker's lower bound here and find all C's, find all n and m such that the lower bound is smaller than or equal to C. Okay? So the left-hand side grows very fast. That's the point, whenever it's not 0. And let me make one comment. So the big deal here is that everything is effective. It's possible to get non-effective bounds on even sums of more than 2 things using S-units theorems. So these lambda and mu, they have lambda to the n, lambda mu to the n, they have their prime divisors are predictable because they're the powers of this. So you have a fixed set of primes and you have a sum of things whose prime divisors are constrained to S. There are non-constructive lower bounds that give you this. But the big deal here is that everything is completely effective. Okay, so this is how you solve the one when you have 2 guys. And when you have more than 2, you just apply this argument in the iterated way. So let's now take a to the 2 to the n1 plus b to the 3 to the m1 plus c times 2 to the n2 is equal to d. Well, because I use d. Okay, now how am I going to solve this one? I will use the same type of an argument here. First, I'm going to guess which 2 terms are the biggest. So, if the difficult case is assuming that a times 2 to the n1, b times 3 to the m1 is greater than 2 times 2 to the, well, let's do it like this. 2 to the n2. Okay, so I'm gonna guess all possible orderings of these guys and solve each of them separately. So the difficult one here is when the two dominant guys are a power of 10 to the power of 3. If the 2 dominant guys were 2 powers of 2, then I would be able to link n2 to n1. Because imagine this is the second biggest term. Then there's a maximum gap between n1 and n2 that is computed from this coefficient. So if, for example, these guys are all 1, then n1 and n2, the gap between them cannot be 100 because everything else is bounded by the n1, and I can just, it's too small, cannot match the denominator. So the difficult case is always when you have 2 different dominant guys. So then what do? So let's solve this now. So I put these guys to the left side. K minus c to the n2. And I apply Baker on the left-hand side. So these guys grow as fast as basically the dominant terms. So n2 cannot be too small compared to n1. In fact, what you get is that n1 minus n2 is polylog in n1. So what I did was I bound this guy to n1. Okay. Now, what's the next step? The next step is to merge these 2 on the left. So now I write it as 2 to the n1 times A plus C times 2 to the n2 minus n1 plus B times n1 is equal to K. Okay. And this almost looks like what I had at the beginning, is the generalized Pillai equation. But here, instead of a constant, I have something that is in terms of n2 and n1. But n2 and n1 are close to each other, so this will have small height. So what I'm going to do is I'm going to apply Baker again, but instead of now having a height that is a constant number, it's going to be something that depends on n2 minus n1, which is small. So in the end, what you get is that this guy, the left-hand side, whenever it's not 0, it again basically grows at the same rate as well, let's say, whatever this means. So there's going to be, now 2 to the n1 will have some logarithmic terms here, but this also grows very fast. That's the point. And then if there were other terms here, then I would push them in one by one, and I would, in the end, be left with 2 to the n1 and a sum like this, 3 to the n1, that's a sum like this. So what I do is now iterative Baker, and then I put a lower bound on the whole sum instead of 2, just from the fact that when this guy is close to n1, when I perform this merge instead of the fixed constant, I get a constant that grows very slowly compared to n1. So in the grand scheme of all applications of Baker, this is actually easy. It's not, but something is interesting. So in the literature, there are tens of papers that talk about, for example, solving linear equations over powers of 2 and Fibonacci and something else, 2 and 3, like only 3 equations. So there's like a whole industry of papers that all do essentially this trick. Of course, at various stages they care about how efficient this is, because our trick is general, it works for any systems when you have 2 LRs with 2 dominant roots, but the bounds on solutions it produces is terrible. So if you're interested in good bounds, then this is not the way to go. Okay, so this is how you solve a single equality, and I claim that if you can do this and the inequalities, then you have the full existential theory. Okay, so
what do you do if you need to solve equal to 0? Because
yes, very good. So I made a divisibility argument here, right? If this was just a generalized Pillai, I made the 2 and 3 are coprime, so the VP argument. What I do is I do my iterative Baker, I construct these 2 sums, right? And I have so I do my iterative Baker until the very last step. In the end, I'm left with 2 to the n1 something small plus 3 to the n1 something small is equal to 0, and then I make my divisibility argument again. So that's very well noticed. Okay, any more questions about this?
What's the part that prevents this from working for more than 2 hours? That there's no effective version of Baker, or?
Well, Baker gives you something about 2 summons, right? So if you had something about 3 summons, then you could push things into those. You have something about 3 summons, but it's non-effective.
Okay.
Okay. Is there like a way to... No, this has to be discontinued.
you can do it continuous, but then that way and then bring down.
I see.
At least that's what everyone else was doing.
So now I will move on to undecidability and this tau function business. Before that, so this was the existential fragment. To decide the existential fragment, you usually do some number theory. To decide the full theory, I think there are 3, I know of 3 methods. One is quantified elimination. So if you had, right here. So let's just take natural number, class, order, and I'll add Vn, Vn. So a linear recurrent sequence with a single dominant root rho. So in this case, if the linear recurrent sequence is irreducible, then this rho is a per-row number. And in this case, there's quantified elimination algorithm. There's also axiomatization of the theory feature François Poix. And if this rho is a piezo number, then there's this automatic structures argument. So there are 3 different arguments, at least I know, to decide the full theory. But if there's more, let me know. I'm very interested in this. But how do you prove undecidability? To prove undecidability, in any case, you have to reduce from, you take an undecidable problem, and you show that if you could solve your problem, you would have solved the undecidable problem. Therefore, your problem must be unsolvable. So this Hilbert's, if you go by Hilbert's 10th or the new Hieronymus-Schultz method, at the end there is an undecidable problem from which all of this comes down. So what is this undecidable problem? So, given a program P, decide if it terminates. So this program P could be in Python, could be in your favorite programming language, could be a lot of things. But you have to reduce that problem to your problem, so it makes sense to consider a model or a set of programs that are as simple as possible. So the simplest one I know is called a 2-counter machine. So it's a program where there are 2 variables. Let's call them counter 1 and counter 2. And in this formulation, I'll make them take values positive integer values. And the instruction set of the program is increment counter ci. Then if ci is greater than 1, then decrement ci, else jump, to some line L, so the program numbers are 1. There's also this unconditional jump to some line L, and halt. So you start with C1 equals C2 is equal to 1, let's say. You go to the next line, it can say increment, you increment it, you go to the next line, it can say jump, you jump. The important thing is that there's a test to check if something is 1 or not. If something is equal to 1, then you jump. If something is not equal to 1, then you don't jump. So there's just like a branching. And to get undecidability, you need some kind of branching. If you have got like a purely monotonic execution, then you never have undecidability. So the undecidable problem is that you give me a program in this language, and I tell you whether the line halt is ever reached or not. So the sequence of, so the run of this is the following. I use 0 as a separator, so the value of the counter 1 at time 1, the value of the counter 2 at time 1, and the line number at time 1, then another 0, then the value of the counter 1 at time 2, the counter 2 at time 2, line at time 2, 0, and so on. So there's this, the run of the machine, right? So halting is the same thing as saying that the run is finite. Okay. So this is the problem from which we will be reducing. And the idea is that in these structures, there exists a machine, a first-order machine, with finitely many inputs. You plug these finitely many inputs, and out comes sequences, finite sequences of natural numbers. And this machine is onto, so you can generate any finite sequence of natural numbers from finitely many inputs. And then you give me a program, I write a formula that says that there exist finitely many inputs to this machine, such that the finite sequence that comes out of it is a halting run. Means that it has this structure of 0, 3 non-zero numbers, 0. These guys are updated correctly, and it ends in a halt instruction. It's a very common thing in computer science. Okay, so now let's talk about how you extract arbitrary finite sequences from this tau function. Well, 99% of the work is done already in a different paper, so I'll just give you this result. So this is by Bimo and Desulier and Luca. Well, let's just K. A permutation. Okay, there's a caveat. So you assume that assume tau n is not 0 for n greater than 0. So we live with this assumption. It's checked for very large numbers of n and is believed to be true. So under this assumption, for any permutation, there exist infinitely many A such that tau of A plus sigma 1 is less than tau of A plus sigma 2 is less than the absolute value of tau of A plus sigma k. So it means I can extract arbitrary permutations from the tau function. Once you have arbitrary permutations, then extracting arbitrary finite sequences is not too difficult. But with this, the tau function, maybe I should at least tell you what it is. So if I have tau n, if I view it as a tau series, this will be q product n greater than or equal to 1 minus q to the n 24, the sequence of Fourier coefficients of a modular form. And tau 0 is 0, but tau of n for greater than 0 is believed to be non-zero. So Fourier coefficients of a modular form. Okay, once we have this thing, how do we extract arbitrary finite sequences? Well, let's take A, B, C. Actually, A is less than B is less than C. So this defines a finite sequence un, where n starts at B and ends at C minus 1. And u of n is simply the cardinality of tau x, such that A is less than or equal to x is less than or equal to B. So I have three numbers, A, B, C, and basically, first I look at the absolute values of the tau function from A to B. So they fall somewhere here. Let's say tau A falls here, tau A plus 1 falls here, tau A plus 2 falls here. Okay, so these are the guys from A to B. These are ticks on my scale. And then I start looking at, okay, where does tau B fall? So let's say tau B falls here. And I count how many of the other type of guys are less than me. So there's two. So the first term in my sequence will be 2. Does this make sense? So I use the guys from A to B to build a scale, and the guys from B to C, I just look where they fall and I count how many of the orange guys are less than that. And the good, there's a reason why it works like this, because in this machine, what am I going to be checking that it's a valid run? I'm going to be checking that the two numbers differ by 1. right? And I need to check that something is either equal to 0, something that's equal to the halting instruction, and to say that the run is really a run, I need to say that, okay, this guy is this guy plus 1 if the instruction was increment. So I need to be able to check if the two numbers differ by 1 using first order logic. And tau b, and let's say tau b prime, they differ by 1 exactly when there exists a unique guy from the second type between them. So I can express u b minus u b prime is equal to 1 using some kind of a formula, if and only if, some formula phi of tau b and tau b prime holds. So there's a way to check, well, wait, what am I saying? Is equal to 1 if and only if. So I have this A, B, C, they define a sequence, and I can check whether two things differ by 1 using a formula. Okay, that's all there is. So how does the reduction work? You give me a program P, I write a formula that says, let's write it somewhere here. I say that they exist A, B, C such that if I take any, so the part is divided, so for all, let's go this B1, put B6 in B to C, if the number defined, if U, well, let's make them order as well. If the number defined by UB1 is 0 and UB4, wait, 1, 2, 3, so now I need 8, sorry. If B5 is 0, then something happens. So it means that if I have got this ABC such that whenever I take 8 consecutive numbers, if the first one is a 0, and if the fifth one is a 0, this guy is the correct one, correct successor configuration of the other guy. That's the reduction. Okay, so yes.
A new definition of UN on the right. How does it depend on N?
Which definition of UN? This one or
no?
This one.
Yeah, above that. You say UN is the number of.
Sorry, it's UB.
Okay.
Is it UB? Let me see. No, UN. Wait a second. So the UN is number of taus less. Well, yeah. So this is. Sorry. Wait a second. I count the number of taus that are less than the tau. So I count all the taus from the other class. Sorry, that was that. Yes. So this is what I do. So tau, for example, of B prime, I count the number of tau values that are less than me. But these tau values come from this interval. Does it make sense? Mm-hmm. These guys are the
absolute values on the tau n?
Yes, you need absolute values on the tau n. I have one of it. Okay, yes, you need absolute values of tau n. In fact, yeah. I identify the tau function with its absolute value in this law. Anyway, okay, so any other questions?
What's the role of the C? C
The
picks
role of the
the
C, it's just
the number
the
of
length of the sequence. You can even not have C if you want.
Mm-hmm.
Okay. So, there is actually, I'll give you my I'll tell you I just mentioned another result here. So, theorem, bunch of people. well, okay. These are my co-authors, so they will not be insulted by this. So the monadic second order theory of natural numbers with order on the 1 to the n, then the d to the n is decidable. So instead of plus, now I go from first order logic to monadic second order logic, and here I can have arbitrarily as many powers as I want. So there's a caveat in this result that when d is less than or equal to 0, this is a completely normal decidability result. I can write down the algorithm. But when you have more than two things, there exists an algorithm. This algorithm inside it hides the ideal of all polynomial relations between log lambda 1 to log lambda d. This, if we assume Schein's conjecture, of course we know what this ideal is. And this ideal has a finite representation. So there's inside this algorithm, there's this finite object that I don't know how to write down, but it exists. Hence, there exists an algorithm that decides this structure. Or if you assume that 1 over log lambda 1 to 1 over log lambda d are linearly independent over rationals, then again you have a normal decidability decidability. Okay. I think that's all I wanted to say.
Okay.